Okay, so this is the first video in this topic, thermochemistry. Also considered to be dealing with the energy associated with chemical reactions. So just a short video to start with. I'll use a few of these keywords as we go, so keep your ears open for when I use those, and make sure you have an appreciation of what they mean. So we might as well get started right into this. So first of all, the nature of energy in the chemical context, we do want to make sure we realize kind of what's happening in terms of how we associate energy with chemical reactions. So here we have two fairly straightforward compounds: sodium, which is a solid under standard conditions, and chlorine gas. And so if we were to mix these two, we're going to get a reaction, and we're going to generate sodium chloride, and that's a solid. And so in the process of this reaction, we take apart sodium. So we break those metallic bonds. And so there's an energy associated with that. Those bonds are pretty stable, so we got to break them. So that's an energy associated with that. With chlorine, we break covalent bonds. And so when we do that, we have to we need energy to do that as well. Well, what's the product of all this? If we put these together, we generate sodium chloride. And so we know that sodium chloride is a solid at room temperature. Well, what about the energy? Well, there's also an energy associated with sodium ions and chloride ions coming together. And so that is the energy of bond formation. So if bond breaking requires energy, bond formation must release energy. And so the nature of energy in the chemical content is that in many reactions you have to break bonds, and that requires the input of energy, and you also form bonds, and that ends up releasing energy. And so there's a balance between those two. And so this is how we end up with endothermic and exothermic reactions. They're not the same. If they're not the same, there must be more energy required or more energy released. Now, if we wanted to go back, so here's some solid NaCl again. So that's what it looks like in crystalline state. We can go back that way, and again, we would have to break those ionic bonds. And if we broke those ionic bonds, we could reform chlorine gas and sodium solid. And I'll tell you right now that the production of sodium chloride from sodium and chlorine is exothermic. So the production of sodium solid and chlorine gas from sodium chloride is endothermic. So that would be a net requirement of energy. But what if we put it in a glass of water? If we put sodium into a glass of water, sodium chloride into a glass of water, it dissolves. And so you know this process by now pretty well, I hope. There's a hydrated sodium ion. So actually that doesn't look like a hydrated sodium ion. There's a hydrated sodium ion. Remember, there's going to be water attached there around the delta negative of the oxygen to that sodium plus, and that's an ion dipole force of attraction. That's an intermolecular force. Now, you might think that that's going to be endothermic because ionic bonds are pretty strong. Well, it's actually exothermic. The dissolution process for most solids is actually exothermic. And we're going to investigate that in the lab, hopefully. So the nature of the energy transfer in chemistry can be relatively straightforward or seemingly relatively simple, but it's not always the way it seems. It's not always that simple. So we're going to look at some of that stuff in this unit. Definition time, you might want to pause your video and either write these down or be ready to pause it after I finish talking about a few things and copy them down. But a few terms you should be familiar with before the end of the unit. So energy essentially is the ability to do work. So that's one way we look at it. The important thing here, unit is joule, and don't forget you might have to convert kilojoules to joules or vice versa. Work also has the unit of joule, by the way. So both energy and work have the unit of joule. Three types of energy: potential energy, energy of a system or a body due to its position or composition. So when we say composition here, we're talking about chemical potential energy. And that's the bonds in the different compounds. Kinetic energy is the energy due to motion. We don't talk about that a whole lot here. Thermal energy, the total quantity of energy, potential plus kinetic of a substance. And we do look at that a little bit in terms of heat capacities and stuff. And I'm going to explain a little bit of thermal energy in a minute. Heat is a verb, to heat something, and really, so that's the transfer of this thermal energy from a warm object to a colder object. So we talk about a thermal gradient. It always goes from warm to cold, so we always warm up colder objects by transferring heat. Temperature is the measure of the average kinetic energy of the entities in a substance. So you can have, obviously, entities are things like molecules. You'll have many molecules in a sample of a substance. They will not all be moving at exactly the same rate or whatever in terms of generation of kinetic energy. They will have different kinetic energy. So temperature is a measure of the average, not individual or to consider not all entities would have the same temperature. Now back to thermal energy. We talked about thermal energy. So a thermal is the kinetic plus potential. And so here we have two different scenarios. So we have this iceberg made of water. It happens to be in the solid state, and we have a glass of water in the liquid state. So we have a solid and a liquid. Now, which one has the greater thermal energy? Well, it's a sum of the two, so we have to consider the two different energies. So in terms of kinetic energy, obviously there's going to be less average kinetic energy in an iceberg. The temperature is lower, there's less molecular movement. So water would have a higher kinetic energy. So water with higher kinetic energy. In terms of potential energy, remember I mentioned potential energy, chemical potential energy is due to the substance. And the substance in this case is water, H2O, but that substance has chemical potential energy in the bonds. So now you have to consider which one of these situations has more hydrogen-oxygen bonds, because that's where the chemical potential energy is. And clearly it's the iceberg with so many more molecules. And so in terms of thermal energy, the iceberg would have a much larger thermal energy than the glass of water, because it has a much larger mass, much larger potential energy stored in the many more bonds. Now, if you had a glass of water and a glass of ice, then the glass of water would have greater thermal energy because they would have the same potential energy if there's the same amount exactly, but the water would have a higher kinetic energy because it's a liquid state, more molecular motion. In that case, two glasses with the same mass of water, one solid, one liquid, the liquid would have the greater thermal energy. So that's thermal energy. Now, two terms that may be new, system and surroundings in the context of energy. And so system is essentially the reaction, and the surroundings is essentially everything else. And so in this particular example here, the system is going to be whatever's happening in the solution in terms of a reaction. And so that could be some sort of displacement reaction or whatever, but it's essentially those chemicals being converted back and forth. And so that would be the system. And so what are the surroundings? Well, the glass round bottom flask is part of the surroundings. The air is part of the surroundings. Pretty well everything else is going to be part of the surroundings. And so we can, certainly if this ends up being an exothermic process, you would feel the glass getting warmer. You might feel some heat coming out of the top of the flask, that sort of thing. So that is all part of the surroundings, and that heat is being transferred from the system. So system to the surroundings. Now this is known as an open system, and it's open for two reasons. well, it's a system because there's the allowance. You can have heat transfer, so heat can move in and out. And so that's why it's a system, but it's open because you can have matter moving in or out. And so open systems are sort of what we see day to day all the time when we get transfer of energy one way or the other. This, on the other hand, is a closed system, and you can probably see why it's closed, because we can still get transfer of heat, but you cannot get transfer of matter. No matter transfer because this can is closed. And I'll maybe tell you a bit of a story about a closed system like this that I had experience with. Now, the more conventional way we see this in open systems, as I said, open systems are more common. And here's a good example. I mean, you're sitting around the fire and you're getting warm. And so what's the system? Well, the system is actually those reactants and products that are being produced in the combustion reaction. This is the combustion of wood in the presence of oxygen. And so that is the system. And the surroundings then are everything else. So that's why my hands get warm, because the heat is being transferred to the surroundings being my air, surroundings being my hands. All of those things, I feel that transfer of thermal energy to the system, to the surroundings. So those are the more common ways that you would experience system and surroundings. Again, you might want to quickly pause the video and have a read of the law of conservation of energy, but in a nutshell, the main thing about the law of conservation of energy is that energy is not created or destroyed, and so when we have a reaction, we take some energy, be it chemical potential energy, and we convert it to different energies. We do not destroy it. We are not losing energy. It's just being transformed to a different type of energy. Finally, last two things I want to talk about are just endothermic and exothermic reactions. And again, I'm sure you're familiar with this, but just to sort of put it into a form that you're going to see a little bit regularly, potential energy diagram is called. This is very simple. And so again, this line represents the energy of the reactants. So this line represents the energy of the products. Notice all potential energy diagrams, the arrow is pointed up, so we have an increase in potential energy as our scale. Numbers don't necessarily mean anything at this stage. And so what we have in this first example is, so this arrow pointing up is in moving from reactants to products, we have added energy. And so if we have to add energy, the products are energetically at a higher level. Here they are, higher on the potential energy diagram. So we have added energy. And if we add energy to the system, that is, as part of a reaction, energy is added, that's an endothermic reaction. So reactants energetically lower than products, energy been added to the system, and that's an endothermic reaction. On the other hand, we have the arrow pointing down now. So reactants to products. The reactants are energetically lower or higher than products. Products are lower. So less energy in the products. That means energy must have been released somewhere. Energy was released to the surroundings, and that's an exothermic reaction. So endothermic and exothermic. You want to make sure you know the difference in terms of potential energy and the differences in energy of reactants and products. And that concludes this video.